All right, hi, and welcome to Stoichiometry Review Part 4. So far in the first three parts, we've done the following. We've defined stoichiometry as using molar ratios to convert from the amount of our given to the amount of our find. And in exploring stoichiometry problems, we sort of broke it down by focusing on mole ratios and mole maps separately. So let's start with mole ratios. Mole ratios there are two types. They're coefficients in balanced chemical equations, and we use those type of mole ratios when we're given a chemical reaction. There are also subscripts in a chemical formula. For example, in NH3, the subscript is 3, and so we use that when we're trying to determine the number of atoms in a molecule or vice versa. The other thing we looked at were mole map equations. So mole maps is a useful tool when you're trying to convert from one unit to moles or vice versa. So for example, you're starting with grams, your mass, and you're trying to go to moles. You can use the mole map to help guide you. Now, the reason why we did all that is because the key steps for a stoichiometry problem involve first, if our given is an amount other than moles, we need to first convert it to moles, and we can do that using the mole map to help guide us. Once we have our given in moles, we want to convert from our moles of given to our moles of find, and for that we use the correct mole ratio. Finally, if we are asked to report our find in a unit other than moles, then we need to go back to our mole map and convert our moles of our find to whatever the desired units are. So we talked about that, and then we also talked about using dimensional analysis as our math tool to help us solve these conversion problems. Now it's time to see one problem, see a couple examples all done complete together, just so we know what the work looks like. So what we're going to do is we are going to look at a couple of examples here, and what I would recommend that you do, these examples are the examples from part A. We haven't solved, from part 1 of the video, sorry. We haven't solved those yet, but as you read the problems, why don't you pause the video? If you think you can solve it on your own, that's the best thing to do, and then you can play the video and see what the work looks like. So let's start with our first problem. How many hydrogen atoms are there in 1.00 moles of NH3? So we already discussed that in this example, the mole ratio will come from the subscripts in the chemical formula. And that's because we're trying to find the number of atoms in a certain molecule. And that's what the chemical formula tells us. NH3 molecule has 3 hydrogen atoms. So for 1 mole of NH3, there will be 3 hydrogen atoms. Okay, so how will we go about solving this? The first step is, if necessary, to convert our moles of given to, convert from our amount of given to moles of given. Now our given here is 1.00 moles of NH3, so we don't need to do that first steps. So notice here that's written as Na. We don't need to do it because we're already starting off with moles of NH3. The next step is to convert from our moles of our given NH3 to our moles of our fine hydrogen atoms using the mole ratio that comes from our subscripts. So 3 moles of hydrogen to 1 mole of NH3. Once we have our moles of hydrogen atom, the last step is to convert from moles of our fine hydrogen atoms to the number of hydrogen atom molecules, because that's what they're asking us here. So we have to use, if we go to our mole map, we would see that we would use a 6.02 times 10 to the 23 to convert from moles to number of things. So what does that work look like? This is what it looks like. We take what we're given, put it over 1, and then we'll multiply that by this first conversion factor, which comes from the subscripts. So 3 moles of H over 1 mole of NH3. Since I want to cancel out moles of NH3, that's why the 1 mole of NH3 is on the bottom, and the 3 moles of H, which I want to find, is on the top. Then once I have that, I have now moles of H here, but I don't want to end in moles of H. I want to convert that to number of H atoms, and so I use this conversion factor, and the 1 mole goes in the bottom so that the moles can cancel out, and I can keep number of atoms. And when I do that, I would find that I have 1.81 times 10 to 24 hydrogen atoms. All right, so that's example A. Let's look at example B. For example B, how many grams of H2 are needed to react with 3.99 grams of N2 in the reaction shown? So we already determined for this, since we're dealing with a chemical reaction, our mole ratio comes from the coefficients in the balanced chemical equation. All right, so looking at our map here, we're starting off with 3.99 grams of N2. So if I want to go from grams to moles, I use the molar mass. Once I have the moles of N2, I want to go to the moles of my fine, which is moles of H2. So for that, I use the coefficients in the balanced chemical equation. Now, once I have my moles of fine, I want to go to grams of fine. So again, I would use the molar mass, and this time it will be the molar mass for hydrogen, or H2, which is 2.02 grams. So what does my work look like? I take whatever I'm given, put it over 1 to make it into a fraction. And then I multiply it by the molar mass. And so the grams are going to go on the bottom here so that the grams can cancel out. And then the 1 mole of N2 goes on top. And then I want to convert from my moles of N2 to my moles of H2. So I would use the coefficients in the balanced chemical equation. Since I want to cancel out moles of N2, the moles of N2, 1 mole of N2 would go on the bottom, and then the 3 moles of H2 go on the top. Remember, these numbers, the 3 and the 1, come from the coefficients in the balanced chemical equation shown up here. Finally, I want to convert from my moles of H2 to my grams of H2, so I would use the molar mass in that case. 1 mole of H2 would go on the bottom, so the moles of H2 cancel out, and then the 2.02 grams of H2, which comes from the molar mass, goes on top. And then that tells me that when I do the math there, I get 0.863 grams of H2. Okay, so before I have you guys do any practice problem, I want to pause for a moment just to clarify the difference between a mole-to-mole versus mass-to-mass stoichiometry, since this came up as an issue on the quiz. What's the difference? So if you look at example B that's shown up top here, which we just looked at, this is an example of a mass-to-mass. How do we know it's a mass-to-mass? Well, in this case, we're starting with mass of H2, and we're trying to find the mass of N2. So we're converting from mass to mass. When you're converting from mass to mass, you have to use the molar mass twice. Once at the beginning in step 1 and once at the end in step 2. On the other hand, if you read example D, which says how many moles of H2 are needed to react with 3.99 moles of N2, this is an example of a mole to mole because we're starting with moles, 3.99 moles of N2, and we're trying to find the moles of H2. So for a mole to mole problem, you don't need molar mass because there's no need to convert since you already have the moles of your given. You're trying to go to moles of fine. So all you need there is just the conversion factor. So the first and the last step, you don't need them for a mole to mole problem. For mass to mass problem, you need all 3 steps. For mole to mole, you only need that second step, which is using the mole ratios to convert. Okay, so there are some practice problems, practice stoichiometry problems. So you should pause this video and in your packet do those problems.